Today we begin the introduction to hypothesis testing. We've referred to this already when we talk about drawing a sample from a population because we wish to make some sort of decision or inference about the population based on what we're seeing in the sample. So this is where we formally do that. So when we talk about drawing inference, we're looking at tests of a claim or tests that involve the population parameters. All right? We wouldn't be talking about tests of the population parameters if we could measure the entire population. We're talking about these tests because we have a sample and we're trying to determine what evidence we have to make these conclusions about the population. Some of this you see with product comparisons, or if you product improvement in advertisements, new and improved. Well, is it really? Okay. Is product A better than product B? Okay. Those kinds of things. Election years are great because you get a lot of pre-election polls. So we'll see a lot of stuff that we can look at in just mainstream publications that are statistical results. Okay, we want to talk about how to test a hypothesis. So I have a very, very simple illustration. Okay, I have a lucky coin and I lost it. And the reason it's my lucky coin is because I can cheat. Because I know if I toss a coin, half the time it lands heads up, half the time it lands tails up. All right, but my lucky coin is lucky because it lands heads up 75% of the time. Okay, so therefore I like my coin because I can win my more than my fair share of coin tosses. I lost it this morning. There between the sofa cushions, I found a coin that looks just like my lucky coin. All right, it's a quarter. I'm from Kansas, so it's a Kansas quarter. All right. Is this my lucky coin? Or is it just one of the many Kansas quarters that are out there? What would you do? Toss it. Okay. All right. Toss it or test it out. Right? Okay. So how can I tell if this is my lucky coin? All right. We're going to test it. How many times or how? How do you want to test it? Okay, how sure do you want to be? That's a good question. All right, so we're going to toss it. How many times? You got to pick something. 16? I honestly can say I've never had that as an answer, but that's okay. So we'll say, so we'll toss it. How many times? So we'll say 16 times. All right. Then what? Okay. What do I got? What am I measuring when I toss it? How many times it lands heads up? So I want to measure. Say y equal to the number of heads. Okay. Then what? All right, my lucky coin. All right, this coin. I don't know if it's my lucky coin. This coin had 10 heads. Maybe it only had 6. Okay, what do? I have to be able to make a decision, right? So how do I make a decision? If the number of heads is larger than 50%, right, then I probably think that this is my lucky coin. Would you agree? How large? Because if it's a fair coin, I should get 8 heads. Maybe. Right? Because there's probability attached to this. It's a binomial experiment, right? So I can figure the probabilities of any number of heads out of 16 tosses. So how many do I look at? So if I have 10, do I say this is my lucky coin? What would you think? Well, if it lands heads up 75% of the time, 12. So if y is 12, then it's my lucky coin. What if y is 13?
Probably still your lucky coin.
So y greater than 12? Y greater than or equal to 12? What about 11? That's more than half. So I have to come up with something. So if we want to say what? If y is greater than or equal to 12, I'm going to say it must be my lucky coin. Okay? How could I be more sure? Increase the number of trials. How many times? Okay. So what about 100 times? So if I change it to 100, am I still looking at y greater than or equal to 12? No. So if I toss the coin 100 times, then I need to come up with a new decision rule for y, don't I? So in that case, you'd come up with what? 75-ish? 74? Where do you draw the line? Okay? That's the idea behind hypothesis testing. Okay? Is we want to be able to test a claim. This is my lucky coin. Well, is that true or not true? I have to be able to devise some sort of way to test it and see if that's the truth or not. Okay? All right, so a few remarks here on the next page. So for our 16 tosses in this illustration, if y is greater than or equal to 12, it must be my lucky coin. All right, so if we saw 14, we'd conclude that this is it. All right. So question 1. Could a fair coin is one that's 50% heads, 50% tails. Could a fair coin have a good day? That means could a fair coin land 12 or more heads out of 16? Yes, fair coin could have a good day. All right. So that is, we could observe a large value for y, but the coin is fair. That's what I mean by a good day. And based on this y greater than or equal to 12 rule, I'd mistakenly keep a fair coin as my lucky coin. Could my lucky coin have a bad day? Again, the answer there would be yes. And what would be a bad day? So that is, we observe that, pardon me, not X, but Y is a small value. And so I would then conclude that what? I'd conclude that this is a fair coin. And I wouldn't keep it, but I'd probably just spend it. Right? So I'm down there at the Coke machine, get my Diet Coke with my lucky coin, and it's gone. Now that's simple, and I'm being silly, obviously. All right, but it walks us through the process of hypothesis testing. Okay, so the process involved with hypothesis testing more formally is this. We formulate two hypotheses, a null hypothesis and an alternative hypothesis. So the null hypothesis is the hypothesis of no difference or no change. It looks like a fair coin. I don't have any reason to believe it's not a fair coin. My claim is that it's the lucky coin, and if it's the lucky coin, it's got to demonstrate or prove itself. Okay? I've got to see the probability behind that. So I have to, so statistically, I compute a test statistic. Well, this test statistic is some measure or some random variable I come up with that I have some experiment, some sort of a performance check that I have to do. All right? So in our case, it was toss the coin 16 times, 100 times, whatever that happened to be. All right? And we count the number of successes or number of heads. That's our test statistic. All right? Some measure. Rejection region or decision rule. How do you come to a conclusion? Okay, so if that number of heads was very large for this number of times you tossed it, so if it was 12 or more in 16 tosses, 75 or more in 100 tosses, right, I have to have some sort of a decision rule, okay, and before I can make a conclusion. Then, based on the performance of the experiment, or the test statistic, based on my decision rule, then I come to a conclusion. Now, the things with my conclusion, though, do I know for certain that I've made the right decision? Well, in each of these cases, we kind of demonstrate that, well, yeah, you could possibly make a mistake. But what we want to do is we want to put probability in our favor. We want to put probability in our favor of making the right decision. Okay? So we want to minimize the chance that we're going to be, minimize the probability of being incorrect or making those kinds of mistakes. So there's two kinds of mistakes we can make. There's two kinds of right decisions we can make, right? Okay, and so we outline those right decisions and those mistakes in the following illustration. Okay, the language used in statistical testing is that you reject the null hypothesis or you fail to reject the null hypothesis. We usually don't say things in terms of the alternative and then that language there. Some people will use, instead of fail to reject, they'll write the accept H naught. Some statistics faculty are very picky about whether you say accept or fail to reject. I am not one of them. Okay. However, so that's more generically how we do it. I'm more concerned that you can write your decision in the context of the problem. That's what I want you to do. I don't care if you call it fail to reject or accept. All right. But we typically say this statement, though, in terms of the null hypothesis. Do we believe the null hypothesis? Or do we not believe the null hypothesis? Okay. So, if we reject the null hypothesis based on sample information, we may be making a mistake. We may be making the right decision. So when does that happen? All right. So there's two different things. H naught is true or H naught is false. We don't know which that is. Okay. If H naught is true and we reject the null hypothesis, then it means we don't believe the null hypothesis. We're making a mistake. If the null hypothesis is true, but our test ends up that we reject the null hypothesis, that is, our lucky coin just had a good day, okay, we're making what's referred to as a type 1 error. Okay? If the null hypothesis is true and we fail to reject it, we've made the correct decision, right? If the null hypothesis is false and we reject the null hypothesis, that also is a correct decision. And then lastly, if the null hypothesis is false and we fail to detect that, we make what's referred to as a type 2 error. Type 1 and type 2 are typically use Roman numerals. Okay, we define some probabilities. The probability of a type 1 error is generally given by the Greek letter alpha. We have control over alpha. The probability of a type 2 error is defined by the Greek letter beta. We have less control over beta. Okay? What we are interested in terms of beta, though, is what's defined as power, statistical power. Power is the complement to a type 2 error, the complementary event. So power is equal to 1 minus beta. And in terms of our headings up here, this is the probability that we reject the null hypothesis, given that the null hypothesis is false. Therefore, power is a good thing. So statistical power says we detect differences that are truly there. In this introductory course, I don't think we don't do enough about power. We'll talk about it from time to time, but we don't do power calculations. But the idea, though, is sponsors, financial sponsors or research sponsors, they want to know, they may ask about statistical power. What kind of power do you have? Okay, can you with what probability can you detect this difference? And they'll name a difference. So can you detect? So what's your statistical power? All right, because if your power is not good, they don't want to support your work, right? So power is becoming more and more of an issue, and so that's something we need to be aware of, even at this very early stage. Computing it is not always easy. All right, so let's move away from our lucky coin example. Okay, we want to make hypothesis tests about population parameters, and where we'll start is with the population parameter mu, or the population mean. All right, we want to make some statement about the population parameter that's equal to some specified value mu naught. So that's why mu naught is usually when you see a 0 subscript, we saw that before with the normal distribution when we defined z naught and those things. All right, so I mean the same thing here. It's some specified value. So we can say that the population mean is equal to a specified value, or it's something different. We could have that it's something greater than that specified value in the alternative, or it's something smaller. All right? This is referred to as a two-sided test because here the value, if the value of y bar is much different than this mu naught value, it could be either much larger or much smaller. Okay, these are referred to as one-sided tests. And where we see that over here is in the rejection regions. So for all of these cases, we compute a test statistic. And have you seen this formula before? Sure. Whenever we talked about those probability statements involving a sample mean, probability that y bar is greater than a specific value or less than or whatever. All right, this is just that transformation formula we had when we talked about the normal distribution associated with y bar. So that central limit theorem discussion, right? Okay, this takes the sample mean minus the hypothesized value, okay, divided by the standard error of the mean. So we could have written it instead y bar minus mu naught divided by standard error of the mean. Right? That's okay. For any one of these scenarios here, this test statistic is applicable to all three cases, so I didn't write it 3 times, probably should have, but it's applicable to all 3 of those. The test statistic is what it is, regardless of whether we're doing a one-sided test or a two-sided test. All right, here I have a two-sided test. Okay, if H naught is true, y bar is going to tend to be a lot like mu naught. If H naught is true, y bar is going to be close to mu naught, and this value of z is going to be what? Close to 0. If H naught is false, y bar can be very large. Okay, much larger than mu naught, and that would result in a very large value of z. If H naught is false, y bar could be very far to the left of mu naught, and that means this numerator would be negative, and z would be negative. All right, so if the absolute value of that z is large, then we would say that is evidence that the null hypothesis is false. Okay? Down here, if you're looking at the right-hand test, is the value of the population mean mu greater than the specified value? Well, if this alternative is true, then y bar is going to tend to be much larger than mu naught, z is going to be large. So we're going to reject for z values that are large only. All right, so the 3 different rejection regions here line up with the hypotheses. For the left side test, here, if the alternative is true, y bar is going to be much smaller than mu naught, meaning that our z-score is going to be negative, right? And so we measure then for a z value that's very far to the left of the distribution, we're going to reject the null hypothesis. Okay, so what are these values here? This z alpha over 2. When you write the probability of capital Z being greater than z with subscript alpha over 2, that means this probability is equal to alpha over 2. Okay? My normal distribution is getting a little lumpy. All right. So when we write this z alpha over 2, that means this right-hand area is equal to alpha over 2. Negative z alpha over 2 is over here. Means that this area is alpha over 2. Okay? In a similar way, when we look at z alpha, that's the probability that z, capital Z, is greater than lowercase z alpha is equal to alpha. And this picture z alpha over here. So the subscript means what is the right-hand area this value determines. Z alpha over 2 means the right-hand area associated with that score is alpha over 2. Z alpha, the right-hand area is alpha. And alpha is this probability of a type 1 error. All right? So let's just pick on this one right here in the middle. So here, this right-hand test, if H1 is true, then the value of y bar is going to tend to be larger than mu naught, and z is going to be extreme. So what's extreme? A z value that occurs with low probability. Low probability, or extreme, then, is this value of alpha. So we typically set values of alpha that are quite small, 0.01, 0.05. Alpha doesn't get very big. Okay? When does this apply? What were the conditions of the central limit theorem? Okay, and so that was that central limit theorem said we didn't have to know anything about the distribution, right? We just needed a large sample. For most of the things we're doing, sample sizes of 30 are sufficient. Some textbooks will say 50. That's not tattooed on anybody anywhere. There's a couple applications we look at where 30 is not large enough. Okay, but for most of the things we're looking at, right now we'll say n greater than or equal to 30. Typically, we don't know what sigma is, the population. Some textbooks write it, and so I include it here. Use sigma if known, and that would be right here. But if you don't know the population mean, you don't know sigma either. So this is realistically what you're going to have in practice. And then, of course, we're talking that we have a random sample. All right? But this part here, that's the central limit theorem, right? It says that that distribution goes toward normality. Where are we using this that normality condition? We're computing a standard normal score, right? And that's because of the central limit theorem. So let's just look at a very basic hypothesis testing situation. Suppose I have a sample of size 50, an observed mean of 127, and a sample standard deviation of 44. And I want to test the null hypothesis that the population mean is 35 versus the two-sided alternative. I'm going to choose my probability of a type 1 error to be 0.1. Okay? So 0.1 and smaller are typical choices for type 1 error. You won't see it climb up larger than that. There are a few applications where it does, but mostly it does not. Okay? So we already have our hypotheses written and our value for alpha here, so what we need is our test statistic. All right? Let me see if I can get a couple things on screen here at the same time. All right, so we look at our test statistic. We have a two-sided test, and we're going to compute our z-score. So it's going to be z is equal to y bar, which is the 127, minus the hypothesized value of 135, divided by the standard deviation, which is 44, over the square root of the sample size, which is 50. So if we compute z, what do we get? Have negative 1.2856. Do you agree? Our rejection region is what? You're going to reject the null hypothesis if your calculated value for z up here has an absolute value that's greater than or equal to z determined by what right-hand area? Alpha over 2. Alpha is 0.1, so that means you're going to reject if z is greater than z determined by right-hand area z of 0.05. So you go to the z table, go to the probability column, look for a value as close to 0.05 as you can, and find the corresponding z-score. What critical value do you come up with? have 1.645. Do you agree? So if we draw that picture, like we learned when we discussed the distributions, (1.645) determines a right-hand area of 0.05. It's absolute z, so we can also look at negative 1.645. This area over here then would be the mirror image, and it also is 0.05. So that means it's 0.9 in between. I don't need that so much. Our calculated value is negative 1.28, which would be right about here. Okay? We said we would reject if the absolute value of z were larger than this. Well, the absolute value of negative 1.28 does not exceed 1.645. Agreed? So what would our conclusion be? That our population mean is not significantly different from 135. Now when you write a conclusion, I want a plain English complete sentence in the language of the problem. Well, this problem I peeled away. There was no context. All right, so this is about the best we can do here. Just population mean, and is it different or not different? Also then in parentheses, cite the value of alpha you use for your test. Then also cite what did you compute? Z equals negative 1.2856. All right, we'll add one more piece of information to that conclusion. All right, put a comma, and I'm going to leave a blank here. We'll come back and fill in one more piece of information. Okay? Now, in that terminology, reject and fail to reject, what did we do? Fail to reject. Agreed? Reject means that we're in the rejection region. We're out here in these tails of the distribution. All right, so in that generic sense, what we've done is fail to reject. Notice I wrote that nowhere on the page. All right, when you report your results, it's got to be in the context of the problem, right? You can't go to boss and say, I rejected the null hypothesis. Boss is going to look at you like you're crazy, okay? Boss wants it in language of the problem. So in here, this class, I'm boss. Okay? I want it in the language of the problem. Now that tells me you understand how to conduct the hypothesis test, and you know how to interpret that. All right? Even though I had no context given here, I peeled away everything and say, okay, here are just the essential pieces we had. Okay, so now then, once we get finished with this one, then we'll add context to it and start building them up a little bit more, okay? Now, when you look at this, you're saying, well, does 127 seem that different from 135? Well, you might think, well, that's not so bad, or that seems, it depends on what you're measuring, right? Depends on what you're measuring. If you're measuring money, if you're measuring the weight of contents being shipped, all those, that has a different meaning, that the difference of 8, right? Okay. What we're looking at, though, is we're making our decision is say, given the observed variability in the data, is this 127 a lot different from 135? Given the natural error variability, right? If the natural error variability is quite small, then this 127 would be much different. But given this natural error variability of 44 for a standard deviation, that difference of 8 isn't so bad for a sample of size 50. Now, then that's the other thing. What happens as the sample size gets larger? Okay, as the sample size gets larger, Z is going to get more extreme, right? As the variability was smaller, Z would get more extreme. So there's different ways then that magnitude of Z changes. So let's finish out this last little piece here. We computed a rejection region, which you don't report whenever you write up your results. You don't report a rejection region. You make a different report, and that's the last number we want to compute for that statement. It's referred to as an observed significance level, or a p-value. Okay, p-value standing for probability. So it's a probability, therefore it has to be some value between 0 and 1. Okay? So what a p-value is the probability of obtaining your observed test statistic or one more extreme. Okay? What would be more extreme for us? All right, here is our negative 1.2856. So more extreme would be farther to the left, since we're in the left side of the distribution. Agreed? More extreme than negative 1.2856 would be area from here over. Okay? So, or the mirror image of it on this side, positive 1.28, and to the right. Okay? So here, our p-value is the probability that Z is small or Z is large, whereas that small and large is determined by 1.2856. How do you find this probability? So our picture is going to look a lot like this one. It's just going to be our values we write down here are different. 1.2856, negative 1.2856. I want those shaded areas added together. All right, by symmetry, I know this piece is the same size as this piece. And so it's easier for me to compute the probability that Z is greater than or equal to positive 1.2856. And then I'll just multiply by 2. Agreed? Our z-scores are only to 2 decimal places, so we need to look up the probability that z is greater than or equal to 1.29 and double that. So look up 1.29, find the right-hand area. And what do you have? .0985 is what I have. Do you agree? And when we double this, we end up with 0.1970. So if the null hypothesis was rejected in this example, there is a probability of 0.1970 that a type 1 error was made. What alpha is we're allowing ourselves a probability of 0.1 in this particular situation. Okay, we're allowing that we're going to falsely reject the null hypothesis 10% of the time. And that's why alpha is kept small. Okay, what we would do is come back to our statement here, and then we would add that piece of information, the p-value in that parenthesis. So when I ask you to write a complete conclusion on the test or on the homework, I'm looking for a complete sentence, cite alpha, the computed test statistic, not the critical value you're looking up, all right, but what you calculate, and the p-value. All right, all of those pieces together make a complete conclusion. Now, in general, it is always the case that if your p-value is less than or equal to alpha, you're going to reject the null hypothesis. Or if you've done a rejection region and you determine that you've rejected the null hypothesis, you better report a small p-value. Okay? If the p-value is greater than the type 1 error you're allowing for, so p greater than alpha, that means you failed to reject the null hypothesis. And the reverse is true. From the rejection region, we failed to reject the null hypothesis as in our example. The p-value we reported was larger than alpha. That has to match. Otherwise, if you get those turned about, you're making some logic errors. Cereal containers are supposed to contain 18 ounces of product. Overfilling the boxes creates additional cost to the producer. 80 boxes are sampled. The average weight of the boxes is 18.15 ounces, and the standard deviation is 0.52 ounces. Are the boxes being overfilled? Use alpha equals 0.01 in your decision. All right, so in this case, we're not going to, alpha equals 0.01 is quite small. We're not going to reject as often as we would if alpha were equal to 0.1, are we? Alpha is smaller. The probability of rejecting is smaller. Okay? And so we're controlling that type 1 error rate because if I am the manufacturer and shutting down a production line costs me money, right? So I don't want to shut down the line unless I have strong evidence, right? The other part of it is so we look at this and go, we're talking about 0.15 ounces here. For one box, that's not a big deal. Okay? But if the average of 80 is 0.15 ounces, how do I read that? Because if I'm overfilling them by significantly, then what happens? I'm losing money. Okay? If I'm underfilling them, I'm going to lose money because consumers aren't going to buy my product anymore. Okay, so there's two different sides to this that we could consider. So here we're just answering the question about are we overfilling the containers? Okay. What's our null hypothesis? Oftentimes when we look at problems, the alternative hypothesis, the research question, is actually easier to find. Okay, so here when we look at this, we're looking right here. Are the boxes being overfilled? That's our research question. We're assuming everything's okay, all right? But the research question then is that the boxes are being overfilled. That translates to what in terms of our population parameter mu? Boxes are being overfilled means that mu is greater than 18. Since it was supposed to contain 18 ounces, right? So this translates to that boxes are overfilled. The opposite condition is less than or equal to 18. That means everything, in some references, they'll just write mu equals 18 always. Equality always goes in the null hypothesis, excuse me. The equality always goes in the null hypothesis. Now, if you write the less than or equal to, or that's okay too. So, but the opposite condition. All right, so we're conducting our test at alpha equals 0.01. All right. What do we do next? We need to compute our test statistic. So our test statistic, we're computing our z-score. Why are we computing z? Because we have a sample of size 80, and we're drawing an inference about mu based on y bar, and y bar was 18.5, and our S was 0.52. Okay, So we construct this using our formula. Find that table if you... Okay, we want the right-hand test here. So it's this one here. We have a right-hand test, a right-hand rejection region. All right, so we have 18.15 minus the hypothesized value of 18 divided by the standard error of y bar, which is 0.52, divided by what? Square root of the sample size 80, and compute z. I have 2.5801. Does everyone agree? We would reject the null hypothesis if what? Our rejection region back up here. We'll reject the null hypothesis if z is large only. Larger than what? A z determined by, we want to put all that type 1 probability to one side, and that's the right-hand side. How do we find the z-score that determines the right-hand area? 0.01. This is also referred to as a critical value. Go to the standard normal table. In the probability column, find 0.01 and find the closest z-score you can. For a right-hand area 0.01, the critical value of z should have 2.33. What would you decide? You can draw the picture here if you need to. .33 determines right-hand area, 0.01. Where is our calculated value? That's in that rejection region, isn't it? Okay, so what's your plain English conclusion? The boxes are or are not being overfilled. The boxes are being overfilled. Cite the alpha of 0.01. We calculated a z-score of 2.5801. And we need a p-value. We'll fill that in just a second. So how would we compute p? P would be equal to the probability of our observed test statistic, 2.5801, or one more extreme. And more extreme would be to the right. Agreed? We don't double it because we were interested in one direction only, overfilled. right? So we need to look up 2.58 because our table only goes to 2 places there for the z-scores. What's the probability of seeing a calculated z above 2.58? 0.0049. Okay, that's what we report up here in the in the conclusion. Change marker here. Now notice the language in the problem here. It said overfill. There are some directional wording here. When you see things like overfill, increase, improvement could be in a higher score. So you look for directional wording in the problem. When it talks about is there a reduction or a decrease, then that's less than a left-sided test. All right. So if you have directional wording, you're going to have a one-sided test. In the absence of directional wording, has it changed? Is it different? That would be a two-sided test, right? All right, a real quick look when we talk about type 1 error. We have a graph over here. Suppose we're looking at a two-sided test. So without writing it as the rejection region, the idea is you're going to reject the null hypothesis if y bar is much larger than the hypothesized value, or if y bar is much smaller than the hypothesized value for a two-sided case. All right. If H naught is true, if H naught is true, is it possible? Then, pardon me, it is possible for y bar to be in either one of those tails of the distribution. Okay. If H naught is true, okay, we could get values out here. Does probability favor that? No. Okay. So in this case, I wrote values for A and B here. They're not necessarily the same distance away from mu. Okay. This one's alpha 1 is this area. This area over here is alpha 2. The combination of those is what we call alpha. Most typically, when we conduct a two-sided test, we choose those tail areas to be equal if we have a symmetric distribution, especially. Okay, there may be some more advanced applications where you would want alpha 1 and alpha 2 to be different sizes. Okay, but most of the time we're choosing alpha 1 and alpha 2 to be equal to each other. Okay, we choose alpha to be small so that we make a type 1 error a very small percentage of the time. Okay, so that, and so what's type 1 error? Rejecting the null hypothesis when we shouldn't. Okay, we want to keep that small. So this is just a little a further illustration, at least for a two-sided test, that we typically choose those tails to be equal to each other. Okay. Now the other thing we can do from our sample, we can test claims about the population mean, but also we can estimate the population mean. And this is also related to the central limit theorem. All right, we know that y bar estimates mu. That's our whole reason for computing the sample mean, is we want to get some idea of what the population mean mu is. So y bar is our estimator. We have that s squared, the sample variance, estimates the population variance sigma squared. Okay, and we have s sub y bar estimating sigma sub y bar. Okay, so we have population parameters, sample statistics. Okay, we want to compute a confidence interval. My shorthand for that is CI, as well as most references. Okay, a CI for our population mean mu. We have these random sample and the same large sample condition from the central limit theorem. So this large sample condition means I can use this Z. That's what central limit theorem's doing. And so here you have an estimator plus or minus a critical value from the table times the standard error. Okay, so we could also write this as y bar plus or minus z determined by alpha over 2 times the standard error s with subscript y bar. Okay, so we form an interval centered at y bar that says we go forward some distance, go backward some distance from this y bar, and we believe then the true value of the population mean mu is in that interval. Okay, couple of notes here. As sample size n increases, my shorthand, as n goes up, what happens to the interval size? As n goes up, so n is in the denominator here, as n gets bigger, this interval gets shorter, right? The interval size decreases. Okay, does that make sense? Sure, if I look at a bigger part of the population, I've got to feel better about my estimate, don't I? I'm going to be able to estimate it better or with a narrower interval. Intuitively, that makes sense. What happens as alpha increases? What happens to the interval size? Okay, we got to either increase or decrease. How do we figure that out? 1 minus alpha, so here's what alpha is. So if we look at our intervals alpha over 2, if alpha gets bigger, this value z alpha over 2 moves to the right or to the left. Alpha gets bigger. If alpha gets bigger, then this z value goes this way. Smaller z. Alpha gets smaller, it comes this direction, right? So as alpha gets bigger, z gets smaller, and so therefore the interval size also gets smaller. If alpha is bigger, my confidence is smaller, right? If my confidence is smaller, I feel less confident about a smaller interval, don't I? I'd feel more confident with a bigger interval. Intuitively, that makes sense. An example, we have a sample of size 50 that has a mean of 72 and a variance of 96. Compute the 95% confidence interval for the true population mean. Okay, so we have n equals 50, y bar is 72, and variance s squared is equal to 96. I want a 95% confidence interval for mu. So 1 minus alpha is equal to this 95% confidence, or 0.95. So that means alpha is what? 0.05. So that I write my confidence interval. I'm going to take y bar. Just a second here. Y bar is 72, using my formula, plus or minus. Z determined by alpha is 0.05, so alpha over 2 is 0.025. Standard deviation is square root of 96 divided by square root of the sample size, which that would be square root of 50. So I need to go to the z table, or standard normal table, go to the probability column, find the values close to 0.025 as you can, and find the corresponding z-score. What value do you have? I have 1.96. Do you agree? 96 over 50, and the square root of that, I have 1.3856. So that means we're going to have 72 plus or minus 2.7158. If you let your calculator keep extra decimal places there, you may get 2.7159 or so. So that means our interval goes from what at the left up to what on the right. Right hand's easy. 74.7158. What is it on the left? $69.2842. Do you agree? So we are 95% confident that the population mean is in this interval. What would the 90% confidence interval look like? What would change? We would still have the mean 72 plus or minus. Our z-score would now be determined by a right-hand area of what? .05, wouldn't it? Because alpha is 0.1. And we're multiplying by 1.3856 still. So the mean and standard error didn't change. Only our confidence changed. A z-score that determines a right-hand area of 0.05. A couple of these you're going to start to recall without having to look up. $1.645. That'd be 72 plus or minus 2.2793. That would be 69.7207 on the left up to 74.2793 on the right. Which interval is bigger? %. I can be more confident about a bigger interval, right? Intuitively, that makes sense. All right, and we could have chosen other confidence levels as well. So what does this idea of confidence mean? So in particular, we'll talk about 95% confidence. What that means is that in repeated sampling, the probability of computing an interval that contains the population mean mu is 0.95 in repeated sampling. So what we have here I drew a curve. We know for n that's large enough that y bar is distributed approximately normally with the mean of mu and a variance of sigma squared over sample size. Agreed? Okay, so say here's our normal distribution. These are all of our possible values we could get for y bar. This normal distribution has a mean of mu that we're centered at. Okay? If I want this middle area here to be 0.95, so what I mean by a confidence interval. So from this vertical bar to this vertical bar here, this middle area is 95.95 or 95%. Okay? By symmetry, we know this area over here is equal to 0.025, and we know this area over here is also 0.025. Total area is 1. Okay? What are these two values here? Okay? So we want to find the two values A and B such that the probability that y bar is between A and B, is equal to 0.95. Well, what is A equal to? A is equal to mu minus 1.96 times sigma over square root n. And B is mu plus 1.96 sigma over square root n. That 1.96 comes from that 95% confidence. You with me so far? Okay, so what does 95% confidence mean? So let's suppose each one of us in here goes to this samples this population. Each one of us draws a sample of size n. We all have the same value for n, but we each have different data. We each have different y bars. Okay, we each have different y bars, so we each compute our own confidence interval. All right, so you take your y bar, and your y bar, let's say, is here. You go forward, you go backward, that same distance. Your confidence interval captures mu. The next person, their y bar is going to be something different. They again move forward this distance here. My drawing perhaps doesn't reflect that. So the width of these intervals are supposed to coincide with this. Should use a ruler better. This interval works. Am I ever going to get a y bar value that's over here? Kind of in the scale of things. Sure. With what probability? Well, I know I'm going to be in the tails of this distribution 5% of the time. So what happens when I have a y bar value over there in those extreme areas? I move plus and minus this distance away from that extreme y bar. So I go, this one comes back. I form its confidence interval, this y bar. This confidence interval misses mu entirely. Right? How many times, how often is that going to happen? 5% of the time, because I set alpha to be equal to 0.05. Okay? 5% of the time the interval misses. 95% of the time the interval captures that. That's the same as the probability we attach to rejecting the null hypothesis when it's false. Okay? And when it's true, rejecting when it's true is a type 1 error. It's that same alpha. It's that same, we know that y bar is going to be extreme alpha percent of the time. I guess 100 times alpha percent of the time. All right, we want to keep alpha small. All right, so when we look at confidence intervals, then in repeated sampling, we know that interval is going to miss 100 times alpha percent of the time. So if it's 99%, I'm only going to miss 1% of the time. If it's 90%, 10% of the intervals are going to miss. In practice, what do? You conduct the experiment once. Right? You do the experiment once. You either test the hypothesis or compute a confidence interval or both. Okay, but you do it once. One sample, one mean, one decision, one interval. Okay? Does your interval work? Is it successful? Is your hypothesis test correct? You don't know. What do you know? Probability's in my favor that it did work. Right? I put probability in my favor. I know that I'm going to only get these extremes a very low percentage of the time. I'm putting probability in my favor. If I could go through this whole course and make a mistake 5% of the time, would I be happy? Yes. Okay? Or 1%. Now, what some areas have to decide then is what is the cost attached to a type 1 error versus a type 2 error. Because the more often I reject, alpha's big, right? Some disciplines then, they look at the cost associated with a type 1 error. So in pharmaceuticals, maybe you're only looking at alpha's never going to be bigger than 0.01. Okay? Other places, perhaps the type 2 errors are more costly, so I can, if I increase the, if I change alpha so that the type 2 error is minimized or made smaller. Okay, so that's all very context dependent. All right? But this is the idea behind confidence and also behind the intervals. So when we end up in these tails of the distribution, our z-scores that we calculate in hypothesis testing are also extreme.